Greetings to everyone. My name is Chinmay Vinay Dandavati. I am currently in the third semester of the MSc Statistics program, and I am pursuing this degree from the Institute of Science Nagpur, which is an autonomous college under the government of Maharashtra. The topic which I have selected to make a presentation on this course of mathematical programming is Big M technique. As compared to the presentations which I have made till now, this is something which has got much more to do in terms of its applications as compared to the topics which I had selected so far for making presentations. It is a topic which has much more technical aspects, many more technical aspects as compared to the topics which I had selected before. So it is a technique, and the main question or the basic question is what is so special in it, and as the name suggests, it is the Big M technique. What is the Big M in it, and why is that Big M so special? So as I have said, it is a technique, it is a method, it is a catalog or a set or a sequence of instructions or sequence of things to do, sequence of stuff which needs to be made functional. And since it is a technique or it is a method, the utility or the fruitfulness or otherwise the futileness of this method can only be checked or can only be understood by applying it in an example, and more preferably a real life situation or a real life example, because a real life example will have some real life consequences, and only those consequences can let us know whether it is fruitful or whether it is futile. So its necessity, its absolute importance can also be explained by the means of a real life industry example. So here we take an example. We have a beverage plant which sells two types of juice carts. So there is cart A, which contains orange juice, and it gives a profit of rupees 3 per box. And let the number of cart A's available for sale on a given day be x1. Card B, which consists of apple juice, gives a profit of rupees 2 per box, and the number of card Bs available on a given day for sale be x2. Now there are certain business strategies, or rather there are certain regulations or certain limitations which must be followed by the beverage plant, and they are as follows. Now the first restriction or the first regulation is that at least one cart of any type must be offered for sale. That is, the total number of rather the total number of carts offered for a sale on a given day, which is of course x1 plus x2, should be greater than or equal to 1, and it is the first constraint. Secondly, each cart must have some minimum contribution to the profit, the total profit which we are going to get on that day. And the minimum contribution, which here is termed as the satisfaction score, is that cart A must contribute at least rupees 1 and cart B must contribute at least rupees 2, and the total satisfaction score from all the boxes given on the sold on a given day must be at least rupees 2. So we have to combine these three conditions in a form of a linear inequality, and we do so by using the concept of inequality and by also expressing the individual profits as coefficients of the variables which are representing those entities. So we get this inequality x1 plus 2x2 greater than or equal to 2, which is the second constraint. Now since the number of cards can never be negative, which is yes, but of course it is very much obvious, we have xi greater than or equal to 0 for all values of I, which is the non-negativity constraint. Now here, if we look at the way in which this situation is put forth. So the entire situation is in terms of profit. The context is of profit. And in any business, the goal is always to maximize the profit. So our objective is to maximize the profit, which has to be shown as a function of profit given by cart A and cart B, which gives birth to the concept of objective function, which is as follows: max of z. Z is the total profit, so we have to maximize this profit. It is a function of x1 plus x2, and if we describe it given the situation in front of us, which is put forth in words, it is max z equals to 3x1 plus 2x2. This is the objective function of this linear programming problem. This is the goal or the purpose which we have to serve. It is put forth in the mathematical language. It is a mathematical statement, and the task of this problem is to find the number of cart A's available for sale on a given day, that is x1, and the number of cart B's available on a given day for sale, that is x2, such that the constraints which we have discussed here, they are also obeyed, and the objective which is dictated by the means of this objective function is also achieved. The target which is in front of us is also achieved, where the target has a linear relationship. Please note this term, it has linear relationship in terms of the individual profits or the factors which are contributing to it. So now the situation is in front of us in terms of words and sentences. Now we have to translate it, of course, to mathematical terms. So we have this objective function. The linear programming problem is as follows. We have this objective function max z equals to 3x1 plus 2x2, subject to the constraint x1 plus x2 is greater than or equal to 1, and x1 plus 2x2 is greater than or equal to 2. Xi is greater than or equal to 0 for all the values of I. Now, as per the normal procedure of simplex method, which is the most elementary method which is used to solve the problems related to linear programming, we subtract the surplus variables from the inequalities to convert them to equalities. Since this conversion of inequalities to equalities is the first step to solve the linear programming problems, so we try to equalize this inequality by reducing this LHS to make it equal to the RHS. So we introduce two surplus variables and we name them as S1 and S2. So we rewrite the constraints as x1 plus x2 minus s1, which is equals to 1, and x1 plus x2 minus s2, which is equals to 2. Now there is this concept of initialization which is to be followed while solving the linear programming problems to know as to what can be the maximum possible value of these newly introduced surplus variables or slack variables if the case is of minimization. And for that we consider these non-basic variables, that is x1 and x2, as 0. And if we do so in this case, we get s1 equals to minus 1, which is very much clear. If we substitute the values of x1 and x2 in this first constraint, we get minus s1 equals to 1, which means s1 equals to minus 1. And if we substitute them in the second constraint, we get minus s2 equals to 2, which of course means s2 equals to minus 2. And we have already discussed, or we have already been aware of this fact, that these variables, since they represent some real life entity, they can never be negative. Them being negative makes no sense. So this violates the non-negativity constraint. But somehow we can't alter the situation which is in front of us. The situation which has posed its face in front of us continues to remain as it is, and we have no power to change it. So now how to tackle with this problem? So to overcome this situation, we have to introduce an artificial variable. This artificial variable, in summary, to say beforehand, is nothing but a false front. It is a false front, it is a sort of adjustment which if we try to interpret physically makes no sense because it is nothing but a way of adjusting and balancing the things. So we have to introduce an artificial variable for each surplus variable. The introduction of the artificial variable is to be done in the following format. Now here I take a bit of digression. I would like to use this opportunity to describe as to how the artificial variables are introduced in a general context. So if there is some linear programming problem with p equations and q greater than or equal to constraints, so there will be p plus q variables for equality constraints. I would like to repeat it. If there are p equations and q greater than or equal to constraints, there will be p plus q variables for equality constraints, out of which p would be the decision variables, or they are also termed as the non-basic variables. They are already present in the problem. Q are the surplus variables, the variables which we have introduced to convert the inequalities into equalities. And in case if the value of these surplus variables turns out to be negative, then we have to introduce an equal number of artificial variables to balance this situation, or to take this situation into our hands, or to put it under control. So now to get an initial basic feasible solution, we firstly consider these p plus q variables as 0 to get the artificial variables of the form ai equals to bi, where I equals to 1, 2, 3 up till n, such that x1 plus x2 minus x3 plus a1 equals to 1. If we talk in terms of the problem which we have been discussing in the previous slide, in the second constraint it will become x1 plus 2 x3 minus x4 plus a2 equals to 2. And now if we consider all these variables, which include the basic as well as the non-basic variables, which means we consider all the variables including the decision variables and the surplus variables as 0, we get a1 equals to 1 and a2 equals to 2, which somehow is within the limits set by the constraints of the problem, but somehow is not the solution of the original problem, because we have made some manipulations here. So if now it is not equivalent, so how to get the solution to the original problem, or the problem to which the solution is desired? So it lies in introducing the artificial variables in objective function with very large coefficients, which are also termed as penalties, denoted by the letter m, such that the artificial variable is removed from the simplex table of the problem due to its large coefficient, converging the optimum solution such that ai is equals to 0. This large coefficient of this artificial variables introduced to equalize the constraints is termed as the big M. And this big M of handling the instances with variables, artificial variables, is the common sense approach. Essentially, the notion is to make the artificial variables through their coefficients in the objective function so costly or so unprofitable or so unrealistic that any feasible solution to the real world problem would be preferred unless the original instance possessed no feasible solutions at all. But then the entire situation itself would be discarded. The situation of that business or that business plan or business idea itself would be considered as a nonsense idea, and it would be discarded. But this means that we need to assign in the objective function coefficients to the artificial variables that are very large. Unlike the slack or the surplus variables, which are having a coefficient 0 in the objective function, we give very large coefficients to these artificial variables in the objective function. Now in fact, this notion is an old trick in optimization in general. We simply associate a penalty value with the variables that we do not want to be a part of an ultimate solution, unless it is unavoidable, as I have discussed in the second point. And indeed, the penalty is so costly that unless any of the respective variables inclusion is warranted algorithmically, such variables will never be a part of any feasible solution. This method removes the artificial variables from the basis, and here we assign a large undesirable, that is unacceptable, unreasonable penalty coefficient to artificial variables from the objective function point of view. Now, if the objective function is to be minimized, then a very large positive price penalty m is assigned such that the profit itself gets neutralized to each artificial variable, and if z is to be minimized, then very large negative price is to be assigned. Now the penalty will be designated by plus m for minimization and by minus m for maximization, where m has to be, of course, greater than 0, and in fact it has to be very large in its magnitude. Now on this basis of background, this preamble which we have seen, or this entire web which we have spun, now we are in a position to arrange all this information in a logical sequence on the basis of this trial and error stuff, or on this basis of examination of all the possible consequences which can be. Now we are in a position that we can arrange all these points or all these conclusions in a logical sequence to devise a procedure or an algorithm of this method. Now this slide which I am discussing right now, it could have been the very first slide of my presentation, because when it comes to methods or when it comes to techniques, the major stuff which is to be dealt with, or the center of the major interest, is the technique, how to do. But many a times it occurs that when we directly, without considering the background or without considering the prerequisite behind it, when we directly come to how to do the things, it is very much likely that we will create some confusions, we will be prone to making mistakes, we will create all sorts of misinterpretations, and we will commit some mistakes. And also there is a good chance, a good healthy chance, that even the person who is studying this can also forget the steps of this method. So when we understand why something is to be done, we need not remember what is to be done. So with this being the philosophy, now I, after looking at the prerequisite, the appropriate prerequisite, now I devise the algorithm. So firstly we take the problem, we convert it into mathematical form. In the very first step, we multiply the inequality constraints to ensure that the right hand side is positive, it should be. And for any greater than or equal to constraint, we introduce a surplus and artificial variable. The surplus variables to equalize the inequality, artificial variables to make sure that there is no unrealistic value of the basic and the non-basic variables. We choose a large positive value of m, and we introduce a term in the objective function of the form m, which is multiplying these artificial variables, and we finally solve the problem using the usual simplex method. And here I would also like to mention, after we get the entire solution, we discard these artificial variables from the objective function in a premeditated manner, in a pre-decided manner, or in a pre-decided strategy. So as we have discussed the algorithm in the previous slide, so now it's the time to mobilize the same algorithm, to execute the same algorithm. So we will continue with the same example of the beverage company, and we will solve the problem using the big M technique. And as we have discussed in the theory, we revise the statement of the problem, including the objective function of the problem and the constraints. So we get the objective function with minus ma1 and minus ma2 as the suffixes to it, and of course there is this non-negativity constraint, and we set up the initial simplex tableau, and I would like to elaborate the basic structure or the skeleton of this simplex tableau. Here there are two rows. These two rows, they represent the artificial variables, or if the problem is not related to the big M technique, then they represent the slack or the surplus variables. Here there are 7 columns, out of which 6 columns are entitled to the 6 variables x1, x2, s1, s2, a1, a2. And there is this 7th column which represents the solution, which is the value which is on the right hand side of the constraints. So, and also there is this additional column on the LHS of this basis, which represents the coefficients of the concerned artificial variables in the objective function, which is minus m minus n. Now, we need to devise, or we need to synthesize one additional row and one additional column. Firstly, we need to devise this column of zj minus cj. So in the simplex table, zj minus cj represents the net contribution or the opportunity cost of introducing a non-basic variable into the solution, out of which zj represents the amount by which the objective function would decrease if one unit of the variable is introduced into the solution, and zj represents the original objective function coefficient of the variable. In simpler words, zj minus cj helps to determine whether introducing a non-basic variable would improve or otherwise worsen the objective function value, depending upon what our goal or our intention about the entire situation is. So the method to find out the value of zj minus cj is quite simple. We multiply the values of the concerned column by the coefficients of the artificial variable. We add them, that is 1 into minus m plus 1 into minus m, that is minus 2m, and we subtract the coefficients of the this variable x1, which is minus 3. Now here it is minus 3 because we have converted this maximization problem into minimization problem for the sake of standardization, and for that we have to multiply the entire objective function by minus 1. So here it is minus 3. So we subtract this minus 3 from minus 2m, thus we get minus 2m plus 3. Similarly, for the second column, it is minus m minus 2m, which is minus 3m minus minus 2, which is minus 3m plus 2. Similarly, in the third column, it is m minus 0, minus 1 into minus m is m minus 0 is m. Similarly, for the fourth column, it is minus 1 into minus m, that is m, minus 0, it is equals to m. In the fifth column, it is 1 into minus m, it is minus 2m. Similarly, in the sixth column, it is minus 2m. So here we get the zj minus cj column. This zj minus cj needs not to be synthesized for the column of solution. Now, after having synthesized all the values of zj minus cj, we need to look for the most negative value of zj minus cj. Now, since here m is infinitely large, so we consider it for the sake of mathematical convenience, for the sake of computational convenience, as let's say 1 lakh. So if we substitute the value of m as 1 lakh into all these available values of zj minus cj, we will come to know that the value of minus 3m plus 2 is the most negative value, and thus the column which corresponds to the most negative value of zj minus cj is the pivot column. I have highlighted all the entries of this pivot column by yellow color, and the variable which is entitled to this pivot column is also known as the entering variable. It enters the basis. Fine. Now, after having found out this pivot column, we divide the entries in the solution by the corresponding entries in the pivot column, that is 1 by 1, which is equals to 1 to get the RHS. Similarly, 2 by 2 to get 1 in the RHS. Here, incidentally, the values of RHS are same, but we have to look for the smallest positive value. Now here it does not make any sense because both the values are same. So we arbitrarily choose a1, the artificial variable 1, the row corresponding to artificial variable 1, using the smallest subscript rule, that is among a1 and a2. 1 These 1 and 2 are the subscripts, so out of these subscripts 1 is the smallest, so we consider a1 as the exiting variable. It will exit. I have highlighted it in blue color, this pivot row. It is termed as the pivot row, and the variable which is entitled to it is the exiting variable. This variable which is corresponding or entitled to the pivot column is the entering variable, and the entry or the element which lies at the junction of the pivot row and the pivot column is known as the pivot element. Here I have highlighted the element in red color. It is 1. So in the uh, consequent table, here we now move to the very first iteration. So in the first iteration, this a1 artificial variable 1 will be pushed out, and this entering variable x2 will take its place. And before that, we also need to do some transformations. We need to alter these entries by some pre-decided rules. So let us see what they are. So as I have said, we need to do some transformations to form the next simplex W. So as regards the pivot row, so we need to divide all the elements of the pivot row by the pivot element to get the identical row, since the pivot element is 1. But as regards another row, we need to do the transformations by using the following formula. The new value, that is the value which would come in the subsequent iteration, it would be equal to old value minus the pivot row value into the given column value upon the pivot element. Now I know that when this formulation is described in generalized form, it seems abstract, but let us try to describe it. Now I am using the snippet of the previous table to describe this calculation. So here I have encircled the original element in green circle, and now here it is the pivot column, and here is the pivot element, which here is 1. 1 minus 2 into 1, which I have indicated this multiplication by this bi-directed arrow. So 1 minus 2 into 1 upon the pivot element, that is 1. This is the new value of a21, which would be plugged into the second iteration. A22 is 2 minus 2 into 1 upon 1, that is 2 minus 2, which is 0. A23 would be 0 minus 2 into minus 1 upon 1, which is minus of minus 2, which is 2. A24 would be minus 1 minus 0, which is minus 1. A25 would be 0 minus 2 into 1 upon 1, that is 0 minus 2, which is minus 2. A26 would be 1 minus 0, which is 1. A27, that is the RHS value, would be 2 minus 2 upon 1, that is 2 minus 2, which is 0. So after having synthesized this value, we substitute them to form the next subsequent iteration of the simplex table. So after having done these calculations, we substitute them to form the next simplex W. And after having done that, we again repeat the same procedure to calculate the Zj minus Cj. We look for the value of Zj minus Cj, which is the most negative. The variable which is entitled to it, that is S1 here, now is the entering variable. We calculate the values of RHS as we have done in the previous table. We get two values, minus 1, 0. But it is a rule that in the column of RHS, the values which are negative or the values which are infinite are to be neglected, because the values of RHS, they directly resemble the values of these variables. and these variables, these are practical entities, these are real life entities. They can never be in negative numbers, or they can neither be infinite. So we discard the negative values and the infinite values, so we have only one value left, that is 0. So the column, this column which now I have highlighted using blue color, it is the this row which I have highlighted using blue color, it is the pivot row. And again this column which I have highlighted using yellow color, it is the pivot column. We get new pivot element, that is 2. Now we again do the same transformations. We have this second iteration, which is the third simplex table. So we get the third simplex table. So here, after forming the third simplex table, which is the second iteration, we again calculate the values of Zj minus Cj. But here now all the values of Zj minus Cj are either 0 or positive. Thus optimal solution is obtained, or it is said that optimal solution is reached now. Here somehow the optimal solution was reached in 3 simplex tables. In some complex problems one might need to do 10, 15, or for that matter even 20 iterations. Here somehow the optimal solution is reached. So the values which correspond to the values of x2 and s1 in this column of solution are the required values. Here x2 equals to 1, s1 equals to 0, and once that we have got the optimum solution, we do not include the artificial variable in the objective function while calculating the optimum solution, as we have discussed in the previous slides. So we substitute the values of x2 and s1 in the objective function to get maximum value of z equals to 2 into 1, that is 2x2. Here x1 is not in the basis, so we consider its value as 0. 3 into x1, 3 into 0, because value of x1 is 0. 2 into x2, here the value of x2 is 1, so 2 into 1, plus s1, which is having coefficient 0, so it would be 0, plus s2, which again would be having a coefficient 0, so its value would be 0. So we substitute these values, we find the final answer. It is 2 into 1, which is equals to 2. And thus the maximum profit that can be obtained with this objective function, and given the constraints, is rupees 2. So after having dealt with such a vast theory, and after looking at its applications into a real life problem, somehow looking at the very nature of this method, it is very clear that it is not a simple method, it is not a concise method, it does not reinforce a clear logic. It has many complications, it has many niches and orifices where one is prone to commit mistakes, and thus there are many shortcomings of this simplex method. So firstly, there is no well-defined value of how small or large this big M has to be. For the sake of convenience, while calculating the Zj minus Cj, and while explaining how to choose the most negative value of Zj minus Cj, I had somehow considered, for the sake of convenience in calculations, the value of M to be 1 lakh. But however, there is no well-defined value of how small or how large this M has to be. Now if the value of M is too large or too small, and there is no uh, definition or no bound to this too large or too small, it somehow increases the computational complications inevitably. Thirdly, in this method, the feasibility of the solution is not known till optimality. Fourthly, if the number of constraints is too large, it needs to be solved on computer, and given the operating system of the softwares and programming languages, they show errors many a times even if the input is correct, due to which the method is not computer friendly. That is, if you try to solve these problems using the programming languages or softwares like, let's say, MATLAB or SageMath, it will show many errors, and thus these shortcomings pave the way for the two-phase method. But if indeed this method has so many shortcomings, and if indeed the method has to be replaced by some other method. So what is the point in studying these methods, and what is the point in me designing any seminar or any presentation on this topic at all? It raises a big question at the very reason why I am creating this seminar. So the reason is quite simple. We are now in the almost the mid of the second decade of this 21st century. The avenues and the arenas of science and technology, they are reaching new heights, but as somebody has said, we are standing on the shoulders of the giants, and we must know where the feet of these giants lie. So this is what I have felt about this seminar as well, and this is just a method, and this is not wholly the entire branch as it is constituted in today's date. It represents rather some past self of this entire journey, which has already joined a long succession of the other iterations and other variations which existed for a while and faded away and left only a memory behind. But somehow we need not to forget this memory, because these are the memories of the mistakes which we have committed. And if we forget our mistakes, we are prone to repeat them again. So we need to know what were the mistakes committed by them, so that we are saved of the lot of time and efforts which they spent to let us know what are the possible mistakes which we can commit. And we are not supposed to commit them. It is just like a lesson which we have to learn. So with this, now I am at the end of this seminar. So it's the time for acknowledgements. So here is the list of all the resources which I have used to design my seminar and to gather the content for my seminar. So it's quite a very, I mean, it's not quite, it is very vast body of resources which I have gone through, and I have presented the crux of these materials into my seminar. So now it's the time to end my seminar. So I thank you for your patient listening, and also for your precious attention, and also for your time. Thank you very much.